Hey everyone, welcome to our second themed month, Mechanical March. We had a brilliant time with Functional February. That's just coming to an end now. Yesterday I recorded a great interview with Louis Pilfold, the creator of Gleam, which was just a really fun interview. If you've not watched that back, I really highly recommend that. And there's also the interview earlier in the month with Jose Vellum as well, the creator of Elixir, which I also highly recommend watching. It's been a really fun month. Thousands of you have been taking part, solving exercises across all sorts of functional languages. But enough with that. Today, we're talking about Mechanical March. And this month, we're going to be focusing on system languages, those that compile down to machine code. So in this video, I'm going to give you a quick introduction to the month, and then we're going to look at the system languages that we're using. We're going to understand their evolution through history, the pros and cons of compiling to machine code, and actually take a look at each of the featured languages in the month. So firstly, I'm joined again by Erik. Hi, Erik.
Hi, Jeremy.
I'll let you do most of the talking in the second half, Erik. But for now, I'm going to get us started with some of the more practical information around the month. So firstly, the featured languages. So the featured languages for this month, they're C, C++, D, Go, Nim, Rust, V, and Zig. You don't have to remember all those. They are on the website. To get the Mechanical March badge, you need to complete 5 exercises in one of those languages. Our Go track has got one of the best syllabuses in the whole of Exercism, so I really recommend you try that out. We're also really big fans of Nim here at Exercism, as it's a relatively simple language to get started with and really easy to write. So I'm definitely recommending trying that out too throughout the month. Just like last month, we've got 5 featured exercises to try. The first of these is linked list. In some languages, that's called simple linked list, slightly different exercise. And that's really interesting for exploring allocating and freeing memory for pointers. We've also got secret handshake, which is interesting for bitwise operators. We've got pangram for for loops, strings, characters, that sort of thing. Sieve, interesting for arrays, for for loops. And finally, binary search, also for arrays and also for loops. So those are the 5 or 6, if you consider the 2 linked list exercises that we're recommending. And there's actually a new badge, which I announced in the update video I did a couple of days ago, which is for completing the 5 featured exercises in the thematic language at some point during the year. So to get that badge, you need to complete all of the exercises in a system language sometime during the year. It doesn't have to be this month. If you just get the normal Mechanical March badge this month, that's fine. But at some point during the year, complete the 5 exercises that I just listed in some of those system languages. And you'll need to do the same for all of the different monthly themes. So watch my update video for more explanation on what that badge is about. We've also got lots of fun things bubbling away this month. We've got interviews with a couple of people from the Go core team that we're just finalising, hopefully from the Rust team and some other languages too. We'll be having lots of live streaming throughout the month, exactly like we've had in February, people solving exercises, learning languages, maybe people adding some exercises to the different languages as well. And we're also going to have some Mechanical March swag that will be landing hopefully a bit earlier than we managed to get the Functional February swag done. So that's enough of the sort of Exercism side. Let's talk a bit about the technical side. So firstly, what are these languages used for? Well, we use them lots across Exercism. Our CLI is written in Go. Our internal track management tool, which is called Configlit, if you're a contributor to Exercism, you might be familiar with that, is written in Nim. And then something like the key library that counts the lines of code in your solutions and puts that on the pages is written in Rust. So why do we choose those languages? Erik, maybe you can tell us a little bit about why we use those languages for that tooling.
I think for the CLI, which is Go, I think it was what Katrina was most familiar with, except for Ruby. And Ruby isn't really a language to do these command line tools that have to be deployed across different platforms. But apart from it being a language that Katrina is very familiar with, Go is actually really suitable towards for these types of CLI-like applications where you have a binary and you want to distribute it over a wide variety of platforms. Go has excellent cross-compilation, so it can compile binaries for these different platforms with ease. It's also very straightforward code usually, Go, so it should be easy for other people to read and to contribute to. And in general, it's very easy to deploy these binaries because Go just builds a single binary. So you don't have to install any runtime on your local machine. So it's easy for people to install locally. And that's, I think those are the main reasons why we wrote the CLI in Go. Configured is written in Nim, as you mentioned. And at that point in time, we had configured written in Go, but we did a major overhaul with V3. So there was a lot that needed to be changed. And I really didn't know Go. And we had trouble finding other people that knew Go so that they could maintain or upgrade Configlet. So we chose to rewrite it in Nim. Nim is a very friendly language. So it basically has the same perks that Go has. So it's easy to get started with. You can do cross compilation, and it packages things in a small binary, which is even a bit more smaller than the Go variant. And in general, it was just a really pleasant language to work with. So we figured that if we would write it in Nim, we would maybe find more people that wanted to maintain Configlet too. Although that hasn't exactly worked out well, but we have some people that have some Nim experience, and I think the code base is actually really nice. So if you do know Nim and you want to contribute, do look at the Configlet code base. We happily take contributions.
Thanks. And what other sorts of places would you expect to find these languages used? You said anywhere where you want to sort of deploy these command line things. What other sort of places would you find them?
I think there are basically three different ways which you can look at there being use cases for these languages. So one of them is where performance is really critical. So you can think of device drivers, games, or even operating systems. These are typically things that really want to eke out every last bit of performance. And these system programming languages are perfect for that. So performance-wise, it's usually people choose one of these languages because they have so much to offer in trying to get the best performance out of your code. Another thing where they shine is where resources are limited. So you can think of embedded resources where you have very little memory available, and you don't want to have this huge runtime that has to be loaded before you can actually run code. You just want things to be very bare. So you just don't want that extra runtime cost that you need to have with other languages. So with these languages, you don't have any of that. You just compile to binaries and they can run as is, which makes them really, really good to use in these constrained environments. And I think the third one is that if you want something to be highly portable, so if you want it to be running on a vast variety of platforms, then these languages are often a very good choice. C basically runs anywhere you can think of. It can run on Mars or the moon. You can run it anywhere. And a lot of these languages have links with C, some even compile to C. And you get all that for free for most of these languages. So they are great if you want to have your code run on different platforms.
And I said earlier, the thing that sort of distinguishes these languages are the fact that they compile down to machine code. Could you explain how machine code is different to byte code? And maybe we'll look at the pros and cons of that in a second.
Yeah, sure. So machine code is basically binary code that your machine can execute without doing any transformation. So you can think of it as just a series of instructions that the computer can execute. So it's very low level. You can't basically get lower than that. But bytecode is an intermediate form. So bytecode can't be executed by the machine directly. There is something else that has to interpret that bytecode and then convert it to actual machine code. So this is called a runtime. And major languages like a Python, a Ruby, a C#, a Java, they all have a runtime. So if you compile one of these languages, or in the case of C# or Java, or you run in case of Python or Ruby, there is a runtime that then converts that bytecode into the actual appropriate instructions for the machine that it runs on. So it's basically a sort of trade-off between being portable. So if you compile a C# application, you get bytecode, and that bytecode you can ship to any platform where there is a runtime. That bytecode remains the same across all the different platforms. It's just that every platform has to have that runtime implemented for it. With machine code, you have to also compile for different platforms, but you compile directly to the machine code for that platform. So without this intermediate step.
So in terms of the wider pros and cons, is there a particular situation where you would choose to do one over the other? You've mentioned there the portability of bytecode, but what are the other pros and cons around this?
One of the pros of using machine code, of compiling to machine code, is that it's usually quicker to boot. So there is no step that the runtime has to take to translate things to machine code, but because that has already been done. So it usually starts up a bit faster. There are ways of, if you run things several times, the runtime can, of course, cache the first compilation step. So it won't have to redo this every single time. But the first time it has to do this translation step. And you don't need that with machine code. So the very first time a machine code binary will be faster to run. Machine code also has a smaller memory footprint because you don't need that runtime being loaded. A runtime is software, so you have to have it be in memory. And this means that you not only have the runtime in memory, you also have to have the source code. So it has to do processing. So there's more going on in terms of using memory and maybe even files if it's writing to files. So compiling to machine code is a more memory optimal approach. It doesn't say that once it is compiled that it is using less memory. So that's not a given. But in principle, it has a lower memory footprint. And then the third one is what I mentioned with the portability. It's also a pro in that machine code, even though you have to compile it for each platform, it doesn't usually need a runtime to be installed on the machine. So you might have some dependency on maybe libc, which is like the core C functions that are implemented, but every Unix machine or Linux machine has that. And machine code usually doesn't need that extra installation step, which makes it very portable because there is no extra work that you need to do to prepare to be able to run that code. And it's also, for example, great for Dockerizing it because the Docker container then can also be really small, which is better for startup performance and security, etc. You don't need that. Every single software that you install on a Docker container is an attack vector. So is the runtime. So if you can do without that, it's good for both your security and the performance. But there are also cons, of course. As I mentioned, you have to be able to compile to all the platforms directly in the machine code. So the compiler has to support that, whereas a runtime, it's sort of where you want to have the logic be. So do you want it in the compiler or do you want it in the runtime? And there are pros and cons to both approaches. There are cases where a bytecode actually performs better than machine code. So one of them is what's called profile guided optimization. And that's when you have bytecode, and what the runtime can do is it can sort of do like a naive approach and it can compile something that works. And then it will start running and running, and it will gather these metrics of, hey, this is called, 20 times a second, and that one is called 100 times a second. So let me see if I can change things a little bit when compiling to machine code for the version that runs more. So a runtime is able to do these runtime adjustments where it can look at how the code is actually being used and then adapt. So it can sort of do a recompilation after X amount of time, etc. And that's just simply not possible with machine code. So it is even possible that bytecode outperforms machine code. But it depends. It's like everything in IT.
Yeah, that's fascinating. So let's take a little look at sort of the general set of languages that we're talking about. I'm interested in how they've evolved. Obviously they started with C and now we've got a lot more newer languages coming through. So let's chat a little bit about how they've evolved, and then we'll do a little sort of language by language breakdown and test your knowledge of each of the different languages. So let's start with C and I guess C++. Do you want to just introduce those languages to us, just very, very briefly, and tell us how C++ evolved from C?
Yeah, so C is a very old language. It is better than just writing assembly, but it's still very low level. So it introduces you have functions, you have data types, etc. There's a lot of stuff that you recognize from modern languages, but there's also a lot of stuff that you don't have with C. So it doesn't have generics or many higher level functions or whatever. C is fairly low level, but that's also a benefit of writing C code. So you're just slightly above the machine code, which means that, well, you have more work to do, but you're also, well, what is sometimes called close to the metal. So there is almost no intermediate layers. So you have so much influence on how things are executed by the machine, which gives you a ton of options to optimize. You also have a ton of options to write bugs because you are so close to the machine that you have to do a lot of stuff yourself, and you can make mistakes. At least I do a lot, but so C has a lot of benefits, but it comes at a cost. It also has, well, one of these bugs is very infamous. It's the null pointer exception. So it's called the $1 billion mistake, where if you have some code that refers to something that's actually not present, it's null, it will crash. And we have a lot of crash. And there are ways to exploit that. And there are buffer overflows because if you have a string in C, it doesn't really have a length or something like that. So you have to have code that knows the length, etc. Or, well, it's hard to work with strings, and it's easy to work with strings in a way that you may not, you may exceed the limits, and that's called a buffer overflow. And that's something that can be used by attackers to gain access. It's not that you can't write safe C. It's definitely possible. But I would argue that it's harder to do it than in some of these more modern languages. So memory management being something that you as a programmer have to do, it's in a way it's very fun because you have you must have a good understanding of how memory works, etc. But it's also a bit of hard work. Of course, with experience, it becomes easier, but it's more work than just having a garbage collector do it for you. So you have to have a good mental model of how the machine and the programming language work to do proper memory management. And then C had been around for a while, and a lot of stuff was written in C. And then we got into object-oriented programming a bit. So we had C++ being developed, and C++ is like C with classes. So it is very reminiscent to C, which is, well, it's in the name, it's C, and then with two pluses. So things were added to C, like classes, but also stuff like generics, etc. And there's a little bit of help with memory management, but it's still fairly low level. And this is evidenced by the fact that both C and C++ allow you to write inline assembly. So that's basically machine code within their code. So you could have, I don't know, a ton of C++ code, and you know that there's this one function that really needs to be optimal, and you can then write inline assembly because you know the best way to do it, and the compiler might not to, even though that's often not the case because the compilers are incredibly clever nowadays. It's hard to outperform the compiler, but suppose you just have that case, you can still write inline assembly, and that is basically showcasing that these languages are still very much targeted towards being optimal and low level and giving you a connection to the machine and how it's being run.
And we're going to be focusing on assembly later in the year in one of the themed months. I can't remember which one it is. I think it's maybe October or somewhere around there. But yeah, so if you do learn C or C++ this month, then you can always try and do a bit of inline assembly and do that later on. So if you've never done C or C++, a lot of programmers sort of consider them as a bit of rite of passage, learning memory management, really digging into that and understanding that. It gives you some really good fundamental understandings that I think are useful in any realm of development later on in the career. So if you've not tried one of those languages, they could be a great language to do this month. It is frustrating. You get some weird error messages. You make mistakes, like Erik says. But there's a lot of tools out there nowadays to help you with that and to try and make that process as easy as possible. So C and C++, we'll talk about both of them a little bit more later. But obviously, there's now a whole group of newer system languages that have evolved out of this, Erik. How have they evolved? What are the things they're doing differently to the C and C++ way of thinking?
Quite a bit of difference between C and a modern language like, for example, a Rust. I think all the modern languages all support some way of not having to deal with memory. So there's one exception, but we'll mention that later. But most of the newer system languages all have some way of the runtime or a reference counting system, or I don't know, whatever. There are different ways of doing that, common ones being garbage collector and reference counting. And they will keep track of the things that need to be deallocated. So with C and C++, you are responsible for knowing when something isn't used anymore and you can free it. But with these newer languages, they aim for you to not have to worry about that, basically. So it's often, I think, if you speak to people that have just learned C or C++, it's the memory management that they find hardest. And that's why these newer languages all have some feature in them where they will do this for you. They will help you. And often they can do an excellent job just as well as you could. So that's one thing. And there are more. I mentioned the infamous null pointer exception. It was originally added because it was easy, Tony Horst said. He didn't originally have it, but he felt like, I could easily add this in a day or so, and he did. And he called it, as I said, his $1 billion mistake. And most newer languages don't want to repeat that mistake. So having to deal with null, the concept of null is just something isn't there, and there are different ways in which you can do that. So the problem is with null that the memory is not cleared, or just cleared. It's hard to deal with, so you have to explicitly check for is this null, is this not null, and it's easy to forget because C and C++ don't really help you with that. They don't say, hey, you forgot to check for null. Maybe some IDEs do, but in principle, their compilers don't. But these newer languages, they often take a different approach, where they have maybe a separate type that represents something that is or isn't there, but it's not null. It always has a value. And then you can inspect that value to basically ask them, is this value there or isn't there a value? And then you can work with that in a type safe way. So you just do away with the entirety of the null pointer exception, or at least have less effort of dealing with it. So, there's more. Shall I continue?
Continue.
So, sure. Okay, cool. The older language like C and C++ have, by default, everything is mutable. So you define a string, you define, I don't know, a struct or an integer, and everything is mutable. So you can change it. You can change its values. That's the default. And it's also very similar to how a machine works, because at a processor level, it's just values in memory, and you can change them whatever. There's no guarantee that values aren't changed. So this is very reminiscent of how a machine executes code. But there are downsides to having everything be mutable. I talked to that in the previous video, so I won't go into this whole mutable, immutable argument. If you like, I would suggest you look into that video. But there's now more consensus in there, at least being a change in the default. So if you have, for example, Rust and VLang, which are newer languages, they both have switched the default from being mutable to being immutable. And that's quite a step for systems programming languages, because mutability really was very pervasive. So you had mutability everywhere. And to flip that around is quite a step for system programming language. But you see that it's becoming more and more of the norm. So and there's also performance benefits, etc. But as I said, I won't go into those. But that's absolutely one difference that you're now seeing. These newer languages, what is interesting is that these old languages won't go away. So much source code has been written in C and C++ that we will deal with it until the rest of the lifetime of the universe. It will never go away. So these newer languages all have to have a good story of being able to work with the existing C and C++ code. This is called interop. So all these new languages all have features that allow you to call or use code that is written in C or C++. So every single one of these languages has a story that is about how to deal with C or C++ code. So this shows you that C and C++ might have competitors, but they will always be there. And we should embrace it and just see how we can gracefully deal with all these older C and C++ bits of code. Okay, and then there's one final thing that I'd like to mention is that that previously C and C++ would just compile to machine code directly, but at a certain point there were other tools too, like LLVM, that you could compile to sort of like LLVM bytecode, and LLVM would then directly convert that to machine code. So this has a couple of benefits. So your language only has to be able to compile to LLVM, and which is called IR. It's an intermediate representation. It's LLVM specific, but it's just one language. And then you get for free everything that LLVM supports. So take Rust and Zig. They compile to LLVM intermediate representation code, and then they get all the platforms that LLVM support for free because they just compile to LLVM. And this is something that's called transpiling, which is transforming, or it's a combination of transforming and compiling. You're sort of compiling from one bit of source to another bit of source, so from Rust to LLVM IR, and then the rest is happening at LLVM. And this is something that more and more languages allow to do. NIM even allows a wide variety of these intermediate compilers. But it's a very interesting strategy, and you see this more and more happening in system languages. And it's also great because if you have multiple languages all using the same platform to build on, any improvement to that platform will benefit multiple languages. So if somebody does an extremely cool optimization in LLVM, Rust will benefit it, Stick will benefit from it, NIM could benefit from it. So that's a really interesting change that we are seeing, where these compilers are now no longer doing everything by themselves, but they rely on other components to handle bits of their compilation pipeline.
Really interesting, thanks. And what about things like macros and metaprogramming, that sort of stuff? Yeah, so that's like an interesting split. So C and C++ allow you to define macros, which are things that are where you can do. It's not entirely metaprogramming like. It's a bit where you have parameterized code almost, where you define a macro, and it's almost like a source level transformation that is happening. So you can use macros for a wide variety of things, like almost like shortcuts. It's a bit like functions, but it's not entirely like functions, because it's almost like generating code. So they are very powerful. They're often used, but they can make code really hard to read. So they sometimes get a bad reputation for that, in that they're powerful, but they can easily be abused, and they make the code unreadable, or at least they can. But they are very useful. And especially with statically typed compiled languages, you don't get much in the way of being able to dynamically do things at runtime. So when the application runs, not as in a runtime, but runtime with a space. So what do these newer languages do? They want to have the benefits of a macro, but they want to do it in a bit more, I would say, structured way. So Rust, NIM, and D all have metaprogramming support via macros, or a different way. There are different names for things and different variations, but they all drill down to the same thing, where you have code that generates code. So
Rust has macros, Nim has macros, and D has, I think it's called templates. My D is slightly rusty, but they have this in a way that's much more sensible, I think, than what C does. It's not just almost like a string transformation. You get, for example, actual AST codes. So if you parse your source code, there will be a structure in the source code, and these macros in these newer languages, they will give you the actual structure of the source code. So you can then analyze that structure to, for example, I don't know, generate JSON serialization code or something like that based on the fields that are in a type. But that's much more fancy and type safe than just working with strings like in macros.
I'm going to say there, Erik, that your quote of "my D is slightly rusty" has got to be the quote of the Mechanical March. I like that. I think we should put that on a swag T-shirt for the month. For those of you that watch the functional February videos, Erik putting it's Erik saying the secret's in the name. It's fun. Became a little bit of a meme. So I think my D is slightly rusty can be the meme for this month. I guess when I think of system languages, I think of them as being really low level. Is that still fair in these modern languages?
Well, both yes and no. I think it depends a little bit on what you compare it to. So if you compare it to C or C++, all these newer languages are definitely higher levels. They have iterators, they have, well, macros are higher level too, and they often have higher level functions, etc. Functional programming is slowly finding its way into these system languages, which is a different discussion, but very interesting. If you look at Rust, you could almost see it like it's a functional system language. There's so much functional history in it that you have option type, result types, pattern matching. There's a ton of stuff that you can directly relate to functional languages. Even though Rust is very, it's not very low level per se, but it's still very, compared to like a functional language, it's very targeted towards how does this work at a machine level. But they have these influence that they take from other languages. So it's not just being able to be close to the methods, also being able to have these nice abstractions. So Go is similar. I think all of the languages are more high level than they were, even though they can still be used to write fairly optimal low level code. You don't necessarily have to write things that way. So, for example, with Rust or Nim, you can write things in a fairly high level way and still have it be very performant, even though you're using features that you couldn't even use in a C. And one thing I almost forgot, Nim and D even have the concept of pure functions, which is sort of anathema to having mutation. So Nim and D have the concept where a function doesn't do any side effects, and it has its return value only depends on its input parameters, and it doesn't do anything writing to, I don't know, console or files or whatever. And I think that's a concept that if you would say that to a C program in the 70s, they would think that's absolutely bonkers, because why would you ever need that? But people are now seeing the benefits of having these guarantees and these splitting things up into pure and non-pure functions, and that you can model things in a slightly different way. So I would say you can still do low-level things with most of them, but you are working at a higher level. You have more abstractions available to you that I think make it more pleasant to work with. But don't hold that against me if you like to prefer if you like your C. So
I guess for people then, if you're watching this and you've enjoyed like pure functions during functional February, if that's something you've experimented with and liked, then maybe give that a go in Nim or in D, and take some of that knowledge forward and move it on month by month. So that's the end of the second part of this video. We've got 3 parts. The second part there, just looking at these sort of languages as a whole and seeing how they compare to each other. Erik's now going to walk us through each of the different languages that we're focusing on this month, the ones we've been talking about. A little sort of, I guess, 5 minutes on each one, Erik. just introduction to each language, but also putting together the longer sort of 45-minute A Brief Introduction to series that you might have seen. Erik did one of those for F#. We've got a few more that will be coming out probably by the time we release this. You'll have had those ones released as well. And we're going to be releasing more of those 45-minute brief introduction videos over the coming months. But Erik's going to take us through now and give us a bit of an introduction to what makes each of these different these languages unique. So, Erik, let's start where it began. Let's start with C.
Okay, let's start with C. I think that was also basically how I started programming. The first program that I ever wrote, I think, was like a hangman version in C. So, well, C has been developed by Dennis Ritchie. It is one of the older languages. It's probably, I don't have hard data I briefly look for it, but it's hard. But I would argue that it's probably the most used language in the world. There is so much software that is written in C. It's incredible. And I think only maybe C++ or maybe Java. Yeah. Well, there's a lot of JavaScript now, but probably it's still C, the most software in the world. And the software, you're using C code all the time. If you're on your Mac, if you're using Linux, Unix, Windows, all will have C code in it. Unix and Linux being almost completely C, and Windows having a bit of C++, but you will be using C code everywhere. A lot of your hardware will be using code that's written in C or C++, but a lot of it is C. So it is, I think, one of the most influential languages ever. Think of the fact that we mentioned things of being C-like languages. So C#, Java, they're all C-like languages because they share so much of what C came up with, as in the curly braces, etc., the semicolons. There's a ton of stuff. It's not necessarily all developed by C, but it was packaged into a whole by C, and it's been adapted by many languages. And if you're developing in new languages, often the very first thing that people will do is, how can I make it such that it's easy for people to get started with? And that means looking at how C did things, because most of the languages, the bigger languages that we have right now, are influenced by C. Not all of them, but many of them are. So it's always a good thing to look at how C did things. As I mentioned before, C has manual memory management. So you have to allocate memory yourself. You have to free memory yourself. So memory leaks are a thing. If you forget to deallocate things, your memory usage can grow and grow and grow and grow. And this can be annoying. It can also be very problematic. So you have to be very diligent when you write your C code. So there are a lot of ways in which you can do that. There are guides that help you. A lot of the software that was written to do very performance sensitive stuff, even drivers that are in, hardware that are in people's bodies, etc. It can run C because it has to run in a very constrained environment. So it is possible to write perfectly safe C code, but you have to know what you're doing. So it might be a bit harder to start out with, but you do have control over everything. And that's also very powerful. You get a good understanding of how the machine works, as I said before. So close to the metal, highly performant. It also runs everywhere. I think there's a C almost runs on every single platform that you can think of. It has been around for a very long time, so people have had a ton of time to build all these platform-specific compilers, and it's perfect for embedded systems for that. So the least amount of memory that you can use by not having a large runtime, by doing everything in memory just as efficiently as possible. So, for example, if you don't no longer need something, you can just free it. You don't have to wait for the garbage collector to collect it. You control when something isn't needed anymore. So you can be highly optimal. And an interesting thing about C is that it is a fairly small language if you compare it to other languages. So there isn't that much syntax in C. So you can, I wouldn't say it's necessarily easy to learn, but there also isn't like this huge huge book of syntax that you need to cover. C does things with fairly few concepts in it. So that makes it an interesting language, I think, where you can see that another pun, where you can see that it's with C, it's not that hard to build stuff, because once you have a brief familiarity with the language, you sort of already know almost everything about it. Of course, there are intricacies everywhere, but it's still a fairly small language.
Awesome. And moving then on to C++, you've obviously told us a couple of things about this already. It's still got this manual memory management, and it added object-oriented support. What other things should we know about C++?
Well, it was developed by Bjarne Stroustrup. It's a successor to C, because you have C++. I mentioned that. It has helped popularize object-oriented programming. It's not that it was necessarily new. There have been object-oriented languages, but I think there's an argument to be made that C++ really helped popularize it, and then that continued with stuff like Java and C#, etc. But C++ is one of the big languages in the object-oriented history. It has more high-level features than C, so it's not just that we have objects, we also have generic programming via templates. It has a module support. So C doesn't have modules. So you can think of a C program as just being a very big module. Whereas with C++, you have namespaces. So you can sort of partition things a bit, and you can do information hiding, etc. There's more abstraction available to you if you do C++. C++ is very, very well known in the gaming world. So if you play games, the vast majority of them will be written in C++. There are other languages to write games in, but many of the bigger game engines are all written in C++. And large parts of Windows have been written in C++. It's also, like C, an incredibly influential language. Sometimes it's what C++ did that languages don't want to do. A good example is multiple inheritance. So in object-oriented programming, you have inheritance, and C++ allows you to inherit from multiple things. That is, in principle, very powerful, but there are some downsides to that. So if you go to some of the other languages, I'll mention them later on, they sometimes mention explicitly that they don't do inheritance. And this is in part because of the lessons that were learned from C++ having multiple inheritance. So you ever rarely see multiple inheritances in the form that C++ had implemented it. But it is influencing other languages. And it had like a pioneering role in that, I think. It still requires you to do manual memory management. I think it's somewhat easier than in C, although you can do the C-style allocation too. But it's still very manual. So you don't have a garbage collector. You still are responsible for handling your memory well. And if you don't, well, it will be runtime errors for you. What's interesting about C++ is that it's still evolving. C is a fairly static language. I don't think there's much added to the C spec, whereas C++ is still being actively developed. So there's a standard, the C++ standard, and I think it's every 2 years or something like that, a new version of the standard is run. So new features are added to C++ all the time. And I think C++ might actually be one of the bigger languages that there is. If you check the C++ standard, it's very big. There's a ton of stuff there. There's a lot of stuff in the C++ spec that is a response to how things were originally done, and that might not be optimal. There are better ways now. There's a bit of type inference, for example, in C++ that there wasn't before. So it's a very interesting language to see how things can sort of change, evolve over time. And it's not a new language. I think it's, like 30, 40 years old, but it's still being actively developed, the spec. So it's definitely not stagnant.
Really interesting. It's fascinating to see something that has evolved over such a long time, and how many people must have come and gone in that language community over that time and influenced it along the way. Moving forward in the alphabet, then moving from C to D. I'm guessing D is built on the ideas of C and C++. How close is it? What's its objectives?
It is sort of close-ish. Was developed by Walter Bright, and he was later joined by Andrei Alexandrescu. It was originally envisioned as a re-engineered C++. So I mentioned C++ did some things well and other things that people didn't necessarily like. So the idea of D was that it would learn from the mistakes that C++ made. And of course, it wouldn't make them again. But when they did that, it turned out that they could also take a lot of inspiration from other languages. So they didn't just focus on C/C++. So in the end, D is similar to C++, but it's also quite different. It has its own identity. And for example, it has a multi-paradigm support where you can do things in an imperative procedural way. You can do things in an object-oriented way, like with C++, but you can even do things in a functional way. So you can see here that functional programming is also creeping into a language like D, which was originally a re-engineered C++. And C++ isn't really a functional language. So I find that quite interesting. Of course, as it should be a better C++, it has to have great interop with C and C++, and it has. And one of the things that I found really interesting with D is uniform function call syntax. So you're probably familiar with, normally you use, if you have a function, you have the name, and then you open the parentheses and you put the arguments within it. But with object, you have the object and then you dot, and then you have the function the method that you call, and then the parentheses and the thingies. So with uniform function syntax, those are basically equivalent. So if you do like a method-like invocation with the object first and then the method name, it's equivalent to just doing the method name and then having the object be the first element, so the first argument. So it's a way of merging those two worlds together, where calling a method or a function are basically the same thing, which they are under the hood, because usually the object is just passed as the first argument. But uniform function syntax, call syntax, is a very neat way of handling that discrepancy, basically, where you can do things in a different way. And it can be really cool it allows you to do chaining. So you can have regular functions, but you can call them as if they were methods. And then you can build this nice pipeline of functions. And it's a very functional way. So as we saw with Elixir or an F#, where you have the pipeline operator, it's somewhat similar to that. So another thing that is really interesting and that C and C++ don't have is that you can have code that runs at compile time. So you could have a bit of code that runs a thing, and it doesn't run it at runtime, but at compile time. So you could bake things into your application. For example, you could read a file and you could store it inside the binary, but it would happen at compile time. So you wouldn't occur the runtime cost of it. So if you ran your application, the file would already be in memory because you would have it would be included in compile time. So a great example that they have on their website is, for example, regular expressions. So when you run a regular expression under the hood, that gets translated to like a state machine, which is a very complex thing. And most languages have a way of caching that after the first call, etc. But what D does is it will create that state machine at compile time. So at runtime, you don't have the downside of having to compile that state machine. It will already be there. And this is a bit of a weird thing for most system programming language. So we have macros, but with metaprogramming, but this is actually running functions. So it's quite a different thing to what other languages do. And there are more languages that have this. We come to them later. So some of the other things that it does is that, I mentioned it supports functional programming and pure functions, but it also has many safety features. So one of the lessons learned from C, C++ is that it's easy to make mistakes. You can write perfectly fine software, but it's still hard to find these little memory errors. And D aims to help you find them, or to maybe even prevent them. So it has memory safety via an @safe annotation-like thing. You can have contracts. So contracts are a very formal thing where you have pre and post conditions and an invariant that will hold regardless. And you can encode that in the language. And you rarely ever see contracts being part of the language. It's things that you see in a lot of papers. So technical papers will have this thing where if you call this function, the precondition is this and the postcondition is this. But in D, you can actually encode that in your program. So I find that really, really interesting. And one of the things that's interesting and that had us do a little bit of a hack in the website is that you have your unit test next to your source code. So if you have a function that adds 2 numbers, you have the test that tests that function next to it. So you can see the implementation and the test side by side. And you can also put them in the same modules. You don't have to do it in the same file. But so this thing of where tests are closely linked to the source code is actually a very neat way of showing you that there are tests. Or maybe you're seeing that, hey, there aren't any tests and I need to be adding them. They're not separate. They can be, but so we had to make an exception in the Exercism website because we don't have many languages that do that, apart from PLSQL. But I think it's a really interesting feature. And a final thing which is different from C, C++ is Unicode. So dealing with different encoding types in C, C++ is slightly painful. And D does that in a much nicer way.
Awesome. Thanks. That was really thorough. I remember when we did the D thing, and I was a bit like, surely there's a way that we can get around this and not have to do this. But yeah, fascinating language feature. I always wonder what happens in situations where you have like a lot of edge cases that you're testing for in the function, and you end up with like one function and like 100 tests in the same file next to each other. It feels like a really strange paradigm in some ways, but I guess a really interesting one at the same time. So moving on to other new languages, and probably one of the hottest languages out there, which is Rust. There's a full video introduction that you'll have done for this, so you can maybe keep some of the detail for that full one, but give us the sort of the big highlight points about Rust and why people should consider trying it this month, Erik.
Okay, I'll try and not spoil everything from that video. Rust was developed by Graydon Hoare at Mozilla Research. So Mozilla, of the Firefox browser. They've done more things, but mostly the Firefox browser. And later on, it was officially adopted by Mozilla, and they use it as their basis for a rewrite of their rendering engine. And after some layoffs, it was now part of the Rust Foundation. So Rust is multi-paradigm, a bit like D, where you can do stuff in different ways. So you can write things in a functional way, in a sort of object-oriented way. We see that we have the influence of C for C++ here, where you can do object-oriented programming, but with some of the lessons that are learned. So there's no inheritance, for example. And inheritance is usually one of the core tenets of object-oriented programming. But Rust doesn't have that. There are different ways of doing that, which I won't be going into. But it's quite interesting that they support object-oriented like programming. So you can see that there is influence from C++, but also evolution. Rust is very popular. Many new tools are written in Rust. We have Rust as our lines of code counter tool. The Gleam language is implemented in Rust. It has also one of the most loved languages in the Stack Overflow survey. As a matter of fact, it's at the top. It's the most loved language for the past 7 years. So once people start doing Rust, they get hooked and they really love it. I find it really interesting because it's not the most easy way to get started with a systems programming language. Rust has quite a steep learning curve, although it's becoming better and better. The thing that really sets Rust apart from the C, C++ languages is its way in which it handles memory. So you don't have to deal with the allocating of memory, etc. But you also don't have a garbage collector. And a garbage collector is perfect. It will do a lot of stuff for you, but there is a performance cost of a garbage collector. And the Rust language is designed to be highly performant, and they didn't want to have that garbage collector cost. So they come up with a very own and unique concept of ownership and lifetimes, and I won't go into that. It's very, very cool. It's also quite unique, but they have found a way to not have you do all that manual memory management, but instead they have a way of you encoding sort of like the rules of who owns which data to prevent those common memory mistakes being made. And Rust can then determine itself when things are no longer being used and then free the memory, etc. And it's very modern. You have it's all batteries included. So C doesn't really have like a package manager or something like that. Whereas with Rust, you get a package manager, you get a build tool, you get a formatter, you get IDE integration. Everything is included in when you install Rust. It has great documentation, etc., and a couple of unique features. It's excellent for concurrency, but I go into that more in the Rust introduction video. So it's nice. A really cool language.
Yeah, I really recommend everyone try it. As Erik says, it has a pretty steep learning curve, but people seem to get really hooked. When I was talking to Louis Pilfold, creator of Gleam, yesterday. So Gleam's actually written in Rust, and he was saying, he feels like he's at the point now where he can just watch television and just be changing his code, and he just knows that he won't make mistakes because the Rust compiler will catch everything, and how easy it is to do that because of it. But so it's maybe worth that steep learning curve, even if it feels a bit intimidating at first to get there. So one language, as I said, we've enjoyed Exercism, and we've used Exercism in various places is Nim. Erik, do you want to give us another brief introduction to Nim and tell us why people should try it?
Yeah, sure. Nim has been developed by Andreas Rumpf. It has very, very good, pleasant syntax. So I think one of the reasons why you should really try it, Nim, is to see if you like its syntax. I personally really liked it. It has been inspired by Python, and Python is, although not everybody agrees, but most people would agree that Python is fairly easy to read, and I would say pleasant to even write in. So Nim has that same look as Python, although it does some things differently. But it's really an expressive language. So it's not a huge language, it's not like C, but it's minimal-ish. So it's not extremely big on the different concepts in the language, which makes it easy to get started with, especially pairing that with the easy syntax. So it's easy on the eye, it's easy to understand. There are just a couple of rules that you need to know. And apart from that, it has great performance. There's different features that I will go into in the NIM introduction video, but it is really good at building small, highly performant binaries. So it's perfect for configlet, for example. It's also quite modern. Like a Rust, it has type inference, and you have tuples and generics, etc. So the things that you might miss if you want to go back to a C. But a modern language almost has to have these types of things. People expect it. And once again, you don't have to do your memory management. Sorry about that. So it has deterministic memory management via a garbage collector, but you can also there are different ways in which you can do it. It has also has an option to do reference counting, etc. So but you don't have to worry about that memory deallocation whole thingy. I mentioned it has two things that D also has, which is the ability to run code at compile time and the uniform call syntax that I mentioned before. So it's interesting to see that there are links between NIM and D too. NIM also has, like Rust, macros. So it has them in a very, I would almost say, elegant way. So it's not that hard to get started with NIM macros, even though macros can be very daunting. And it has a thing that where NIM has also a concept of purity and side effects. So it has ways in which you can detect that type of thing. But it's in general, I would just describe it as a very pleasant language to work with. So I had a lot of fun writing NIM, and that's not something that I can say about every language that I write code in. But I would really argue that NIM is fun to write.
Nice. Yeah, it's definitely been something that everyone that I've seen has written code and it seems to really have enjoyed as a language. When we first started playing with Exercism, it was something that very quickly got traction because of how, as you say, expressive it felt, but also powerful, and also being so, as you say, portable, being a system language. So then that takes us on to Go. Go is one of the languages in Exercism that we have the best learning mode for. So if you're looking to try a language in Exercism, I highly recommend Go being one that you try. We're also the official mentoring platform for GoBridge and the Go Developer Network. So we've got some great mentors on there that love supporting you as well. So highly recommend trying it and getting some mentoring as well. Erik, do you want to give us an overview of Go?
Yeah, sure. I'll give it a go. Sorry, I can't help myself. Go has been developed by Robert Griesmer, Rob Pike, and Ken Thompson at Google. They found that at Google, software construction was sometimes a bit cumbersome and software didn't scale. And they felt like there wasn't any language that they that really supported the way that they wanted to write code. So they developed Go, sorry. Go is mostly an imperative procedural language, so it doesn't go the route of being like this big multi-paradigm language, and that is on purpose. It supports an object-oriented like approach, but again, without inheritance. So you can see the link back to C++ again. The thing that is quite unique for Go is that it aims to be very simple. So the aim was to have one be able to memorize the entirety of the Go language syntax in one's head without having to be a very big, fancy, and remember everything. So it should be easy enough for everybody, basically, to remember how to write Go code. It has a garbage collector, so it has memory safety. You don't have to bother with any of the memory things. It's very fast. Go is it has a very fast compiler, runtime, testing framework, etc. And the thing that is quite interesting about Go is that it's very opinionated. So not only is the language purposefully minimal, so they excluded a lot of features that you have in other languages, just to have it be. Usually, there's only one way to do a thing in Go, and that has a lot of benefits to it, where you don't have to choose. It's fairly easy to get started with Go code because it will be familiar to what you have already written yourself. Go format is everywhere, so everybody does the same formatting, applies the same formatting to their code. But the opinionated bit is there's a Go way of doing things, and there's a separate document, Effective Go, that lists all the different ways in which you how you should be writing your Go code. So it's like almost like a guide on how to be a proper Go programmer. So I quite like that a lot. It has all the benefits of the other languages, like being very portable, and it has great cross compilation. So the ability to compile to different platforms without having to jump through hoops. And it's also a language that has error handling at the forefront. So errors are values in Go, and you have to handle them. So everything that can fail will return an error, and Go forces you to deal with that error in your code. So you can't just forget about it, like you could with when an exception is thrown. So Go is quite it's a very interesting and unique language, I think.
Cool, awesome. Do try Go. Work through the syllabus. It's interesting. I think we say in England that it's like Marmite. I think people either love it or they hate it. But it's definitely something that you should try and give a go to, and definitely interact with some of the mentors as well, because there's a lot of wisdom there that they can share and really help you understand the Go way of thinking. Two more languages, Erik. Neither of them are massively popular, but they're both new on Exercism. They're both up-and-coming languages. There's a lot of excitement around both of these languages. So firstly, V.
So V or VLang, if you Google for it, it's developed by Alexander Medvednikov and later on joined by Delian Angelov. And it's a Go-inspired language. So it shares many of the characteristics of Go code. So it has the saying, there's only one way to do things approach. The same minimal syntax strategy. So they mentioned that their entirety of their grammar of their language is just 500 lines of definition. I'm not sure if that means much, but it does say that the syntax isn't that big. So it's very similar to how Google's approached the design of Go. It also has co-routines. They're not called Go routine, but co-routines. Mm-hmm. So that's a feature where you have great concurrency without having to deal with a lot of locking, etc., to have it be performant and safe. So you could almost see it like a redesign of Go with bits left out that they felt they didn't like, and they kept most of the core of Go intact. So if you know Go, its syntax will be very familiar. But they do some things differently from Go. So, for example, they don't have nil /null, but they have a result type. They have the default be immutable, like a Rust, whereas Go has mutability by default. And they have some types, which are a way of combining different types into a single type. They have string interpolation, which Go doesn't have. They say the runtime is smaller and the binaries are smaller. I'm not sure how much difference that makes to you, but you can check it out and see if it's enough of a difference for you to care. They have pattern matching, which Go doesn't really have. And then there's a couple of stuff that they are working on. They currently have a garbage collector like Go, but they are also aiming for a system where they don't have a garbage collector, but something else that's more similar to, for example, what a Rust does or a NIM does. But they are not there yet. They have zero cost C interrupt, according to the documentation. So again, you see the ability to interrupt with C code is still very important. This is a new language, but still one of the things that's really prominent is interrupt with C. They have documentation be generated from code, etc., and a very fast compiler that uses little memory. So if you need to compile stuff on a very constrained platform, VLang is great. And if you like Go, I would just suggest to try VLang and see if you like the differences or not. But it's instructive to see what they felt, the things that they didn't like about Go and the things that they did like about Go. So you can see if you agree with them or not. But it's easy enough to compare these two, because if you know Go, you probably know 80% of the VLang syntax.
It's amazing to see languages like Go already inspiring other languages. Like how quickly that happens nowadays. Cool.
Yeah.
So final one, Zig. Tell us about Zig.
Zig has been developed by Andrew Kelly. It also has fairly little syntax. So it's also interesting that some of these languages are quite big on syntax. For example, C++ and Rust, whereas languages like Zig and Go and VLang and C have relatively little syntax. So there are arguments in both favors, of course, but I quite like the less syntax approach. It also has compile time execution. So another tick on that for that box. It aims to be, as they call it, obvious. So no hidden control flow structures like exceptions or etc., or no hidden allocations. There's no macros or meta programming. So their aim was to create a language where you can, just by looking at the code, you always know what it does. There's no surprises anywhere. So I think it's definitely an admirable goal. They do have manual memory allocation. So this is different than most of these newer languages in that they want you to handle memory yourselves. They have some ways in which it's different from the C++ languages, whereas you can use allocators. So they have like a thing that can allocate memory for you. And you can have different versions of that depending on where you want to store things. And every standard library function that allocates takes an allocated parameter. So it's very, the memory management aspect is very upfront here. So it's not, you don't have to care for it. No, you do. So you really have to care for your manual memory allocation. So you have to think about when do you want to release things? Where do you want to allocate things? Is different from most of these other new languages. So that's quite interesting to see why they took that approach. Their testing framework, by the way, it can detect memory leaks. So that can be really useful because manual memory management is hard. So it's quite likely that you have memory leaks at some point, but the ability to have the test framework detect that is really useful, I think. So it's a great feature. Like a Go, errors are values and they have to be handled in your code. You can't just ignore them. But they don't use null. They use an option type. So again, that's something that's really familiar to functional programmers, where they have a separate type to represent a value potentially not being there. Like the test can be written in the same source file. I don't think the Zig track does that. So lucky for us, we didn't have to make an exception, but it can. So it also uses LLVM as the backhand, like I mentioned before, where you get all the benefits of the LLVM, the tool. It can even compile C or C++ code. So not only can the compiler compile Zig code, but it can even compile C or C++ code. So you can use it as a drop-in replacement for your C compiler. There is an issue with configure that we might use Zig to do cross-compilation because Zig is great at doing cross-compilation. So we will use Zig as the compiler for the C code that NIM generates. So it's really, it's weird. But you can see that you can sort of almost mix and match these things now. And of course, it has easy C interop, yeah. So it does things differently from other newer languages, especially the manual memory part is I found really interesting.
Awesome. That was really interesting. Thank you so much, Erik. So that was the last of the languages. I imagine everyone's brain now is pretty full. Mine definitely is. If you've managed to stay with us throughout the whole of this and watch to the end, both congratulations and thank you. A lot of the information Erik's been put in there, he's putting into these brief introduction videos where he's also doing some code samples, maybe solving some exercises as well as part of those introductions. So do keep an eye out for those introductions as you're watching the video and as you're starting the track rather on Exercism. Yeah, I hope you have a really fun mechanical march. We would love to know which languages it is that you're interested, which ones you're trying. We'd love your feedback. So please paste comments below this video. Also at the forum, please jump on the forum and tell us what you're doing as well. If you've got questions or ideas for how we can improve tracks, or maybe there's even new language tracks that you would like to see that fit into this category, please tell us that as well. We're always looking for people to help build new tracks. Thanks so much for watching. Thank you so much, Erik. That was just amazing by you. Thank you. And I hope everyone has a great day. Thank you for watching. Goodbye.